So, good evening, students. We have been, I think, studying continuous system for last 6 lectures. This is relatively new, so I need to go to more detailed steps in the eigenvalue problem. So, till now, if we recapitulate, we initially started with the beam or Timoshenko beam formulation. We got the equation of motion, but we did not solve the eigenvalue problem for that. But we went for the simpler cases of the string or the axial vibration of rod and the torsional vibration. In torsional vibration, we saw some more complexity in the boundary condition, where we had the eigenvalue appearing in the boundary condition. Today, I'll take one more example on that, and then I will switch over to the bending vibration of beam. We already have the equation of motions and boundary conditions from very first class of this particular chapter, and then we'll go for the solution of the eigenvalue problem. So initially, I will take up one more example. Okay. Okay, so I'll take up one example. So this is axial vibration of the rod, and there is a disc at the free end as we had for the torsional case, but there is an additional torsion, the axial spring is there. So this two ends are fixed support, and the mass of the disc is given. The rod is having distributed mass, so we'll consider the shaft as the continuous system, and there is a disc and a spring at the free end. So while vibrating, not only this mass will have vibration, but also the spring will compress. So they will be giving additional kinetic energy and the potential energy, which we had in the axial rod case. So kinetic energy for the continuous part from 0 to L is given by this, and additionally we'll be having the kinetic energy half mass of the disk and the velocity square at the x is equal to L. So whatever the velocity of the beam at the x equal to L is there, that will be the velocity of the disk in the axial direction. So this is the additional kinetic energy part which we are adding. And then in the strain energy, this was the strain energy earlier for the continuous part, and because of this spring, additional strain energy half ku square, where u is of the displacement at the free end, so at x is equal to L. So this is the additional potential energy of the strain energy will be there. So once we have the kinetic energy and potential energy, the Hamilton principle we can able to apply, and we can get the equation of motion. So those steps I am skipping here. So equation of motion will remain same. Only change will be the boundary conditions because of these two, the spring and the rigid disk. So the boundary condition part will give this equation, which has two components. One is at x is equal to L. These two are at x is equal to L, and this is also one component is at x is equal to L. So those three components at x is equal to L we can separate, and the x is equal to 0 component we can keep here. So the whatever the previous problem is there, at x is equal to 0, we have displacement 0. The axial force will not be 0 there. So this is one of the boundary condition. In the second case, the free end, so displacement at x is equal to L is not 0. So the term within the bracket will be 0 at x is equal to L. So these are the two boundary conditions. The displacement is 0 at x is equal to 0, and this term is 0 at x is equal to L, where this is the axial force on the beam, and this is the inertia due to the disk, and this is the spring force at the free end of the beam. So this the governing equation remain the same, only boundary conditions are changing. Because the governing equation is same, the solution form of the solution which we assume earlier for the axial rod case will remain same. It will contain two constants, C1 and C2, and sine beta x, sine cos beta x. So beta has been defined here in terms of the parameter of the system. Because beam we are considering uniform, so this will be the general solution which we had previously only. So C1 and C2 will change now because of the boundary condition which we need to obtain. So if we apply the first boundary condition in that at x is equal to 0, u is 0. So if we put here, this sign will become 0, only CT will remain, and that equal to 0 means we will get the C2 is equal to S from the first boundary condition. Second boundary condition I am explaining in two parts. When let us say disk is not there, only the spring is there. So corresponding M and the velocity terms are not taken here. In the subsequent slide, I will take that also. So here, this is the boundary condition at x is equal to L. If and because it involves the derivative of the solution, and it's this, and we know that C2 is 0. So if you take derivative of that, C2 is 0. So only one term will be there here of the C1 corresponding to C1. So we have just substituted the previous expression, this one, with C2 is equal to 0 to get in the boundary condition. So we got this. Now we need to put x equal to L wherever x is there. So if we put that, we'll get this expression, which can be simplified like this. Here you can see that our aim is to obtain the beta L, which is this equation is a transcendental in nature, and beta L, once we get from here, we can get the natural frequency. So let us say we solve this equation using numerical technique, and we got the various value of beta L. Then for r is equal to 1, 2, 3, because we'll get infinite number of solutions for this. So once we got the beta RL, and then we can, because we know the relationship between the natural frequency and that, we can able to get the natural frequency like this, where only we need to put the beta or L value from this equation, and they will not be very integer multiple of each other if we go for higher order natural frequencies. So this is one of the solution. So this is a frequency equation when we did not consider the disk, only we consider the stiffness, which is appearing here. But if we consider the disk also, first boundary condition gives the same thing. Second boundary condition will contain this, the mass term also. And now if we substitute, we'll get three terms in that because we need to substitute for here also. So, and once we put x equal to L at respect to x place, we'll get this equation. Now here you can see that omega square is also there. Omega square is the natural frequency which is coming in the boundary condition because of the disk. So because other term is there in the terms of beta, so we need to convert this omega square using this relationship in terms of beta. So that has been done here. So now all the terms of containing omegas we convert into beta only. And now this, if we simplify, we'll get a frequency equation like this. So this is a more complex frequency equation in which we need to solve for beta L. This is a transcendental equation. So, and once we have various solutions of this, then this relationship can be used to get the natural frequency, which has been obtained from the this relationship. So this is another example which explains how additional boundary conditions leads to more complex frequency equations, and we need to go for numerical solutions of that. So here, if we know these parameters, all these parameters, then we can able to solve for the beta L. So we need to know the geometry of the beam and the property of the material property of the beam to solve this. Okay, so now we'll switch over to the bending vibration of bar. So till now we considered either the beam is vibrating axially or in torsion, which is about its own plane, it is having motion. Now we want to consider the bending of beam in which this beam is vibrating transverse to its axis. So this the arrow is representing that the beam is vibrating up and down here. This is a cantilever beam for just for example I have taken. At present, we are looking into the eigenvalue problem which we formulated earlier. So here the complexity is there that the order of differentiation is 4. So earlier equations, whatever we have solved, that order was 2 only. But other side, the mass is having no derivative here also. So that side, there is no complexity. Boundary conditions which we can have, general boundary condition, geometrical boundary conditions we can have, like for this case, we have displacement 0 at x is equal to 0. So here displacement is 0. Even the slope will be 0 at here. So the slope at x is equal to 0 is 0. So at one boundary at x is equal to 0, we have these two. But if you see that x is equal to L, for this particular case, we know that the bending moment and the shear force are 0. So these boundary conditions will be valid for that. So this is the bending moment at x is equal to L, this one, and this is the shear force at x is equal to L. So for cantilever case, this first two boundary condition and this last two boundary condition will be valid. But these boundary conditions are showing that what are the other possibility for if we have free case of beam or both side fixed, then other cases can be there. So we have basically two boundary conditions which are geometrical in nature. One is the displacement and its slope. Another is the natural boundary condition, which is bending moment or the shear force. So depending upon the boundary conditions, we will be choosing them. So this constitutes the eigenvalue problem, this equation and the associated boundary condition. Now let us compare this eigenvalue problem with the general operators which we define. L operator, here L operator will be fourth order differentiation. This M operator will remain same. Lambda we are defining as omega square. So here we have 2p is equal to 4. So p2 will be 2. Q anyway is 0. So p is here 2 because 2p is equal to 4. Now at each boundary, when we are saying x is equal to 0, there is one boundary. We'll be having two boundary conditions because p is equal to 2. In previous cases, we had the only one boundary condition at the one end. Similarly, at x is equal to L, we'll be having another two boundary condition. For cantilever case, this is corresponding to the displacement 0. This is corresponding to the slope 0 because slope contains one derivative of the displacement. At the free end, we have bending moment 0, that is corresponding to that. And this is shear force 0, corresponding to that operator we have. So you can see that also in boundary conditions, what is the highest order of differentiation? Here we have 3. 3 is the highest order differentiation, and we already earlier explained that in the boundary condition we can have a maximum order of differentiation 2p minus 1. So 2p minus 1 is equal to 3. So that is satisfying our general formulation which we described. Now we will solve the eigenvalue problem for cantilever beam case. For different boundary conditions, the solutions will be different. So we are considering the uniform beam. So when we are saying uniform beam, so EI will not be a function of x, so this will come out. M will not be a function of x, this will be constant, that is per unit length. So this equation can be written after rearranging like this, where beta is now defined differently like this, which contain now beam property. So here you can see this is a fourth order ordinary differential equation and this is a homogeneous equation. For cantilever case, we know the boundary condition that at fixed end displacement is 0, slope is 0. At free end we have bending moment 0 and the shear force 0. So the general solution of the eigenvalue problem, which of fourth order differential equation, will be of this form. Because this is a fourth order, so 4 constants will be involved, and that equation will be satisfied by not only the harmonic function but also the hyperbolic function sin h and cos h. So here we have 4 constant to find from 4 boundary conditions of the problem. So these 4 boundary conditions will give us 4 equations to solve for C1, C2, C3, C4. So the procedure is same as we have been doing for the case of string problem or axial rod case. Only thing is here the number of terms are more. So now you can see that boundary condition involve the not only the displacement but the slope. So we need to differentiate this once to get the slope information. Also, because in bending moment we require the second derivative of this, so we need to again derivate this once more. Then in shear force we require third derivative, so we need to integrate differentiate again third time. So this 3 differentiations we need to do so that we can able to apply the boundary conditions which we have. So first boundary condition, which is this displacement is 0 at x is equal to 0. The first one will be coming here. So this is the application of the first boundary condition. We need to put x is equal to 0 and their displacement is 0. So we have put all the 0 at the place of x. So you can see the sign terms will cancel. They will be 0. Cos term will become 1. Even cos h will become 1. So from first equation we got C2 plus C4 is equal to 0. This one relationship between the two constants. Then from the second boundary condition, at x is equal to 0, the slope is 0. So we are equating 0. So here, because now we have derivated this, so here the cos came and sine came here. So now C2 and C4 terms will be 0. So we'll get from the second boundary condition C1 plus C3 is equal to 0. So we got a second relationship between the two constants from two boundary conditions. And then the third boundary condition, the bending moment is equal to 0 at x is equal to L for cantilever case. So at x is equal to L boundary condition. So wherever x is there, we put L. Now we cannot simplify much, so we'll keep this as it is. We'll go for the fourth boundary condition. The shear force is 0 at x is equal to L. So that also we substituted. So now we got this condition and this last two conditions. So here what we'll do, we'll try to eliminate the C4 with C2 and C3 with C1 in these two equations, so that these two equations will contain only C1 and C2. So this C3 will be replaced by C1 from this, and C4 will be replaced by C2 from this. So that last two equations we will change. So you can see that this C3 has been replaced by C1 minus C1, and C4 has been replaced by minus C2. So if we simplify, we'll get this expression. Now this contains C1 and C2 only. Similarly, the last equation of the previous slide, we replace the C3 and C4 so that we can able to express this equation also in terms of C1 and C2. So now we have two equations. One is this, another is this, which contains C1 and C2. These are homogeneous equation. So these two equations can be put in a matrix form like this. So C1 and C2 is here. And now you can see that in the first equation, the coefficient of C1 is this minus this. Now beta square is common, so that can cancel. Minus is also common, so that can cancel. So this will be the coefficient of. So that the first equation is representing this equation, and the second equation is representing this. So beta cube in both terms are there, so they will get cancelled. So now this is a homogeneous equation. So for non-trivial solution, that is non-zero solution, we need to have determinant of this equal to 0. So if we keep the determinant of this equal to 0, we will multiply this with this minus this by this. So this is the determinant of the this matrix. And if we expand it, then we'll see that some of the terms will cancel. Sine square beta L and cos square beta L will add up to give value 1. And similarly, this cos h square beta L minus sin h square, this will also give 1. And these two terms are similar, so they will add up and make it twice. So you'll see that we'll get finally this equation from this. And this is a frequency equation. So as we have obtained earlier, beta L is the contain the frequency. So this is the frequency equation or the characteristic equation, which after solving will get the natural frequency of the system. So here the equations are more in number because of the terms are more, but the procedure remain the same, and we got a frequency equation like this. So this usually will give infinite number of solutions. We need to solve numerically to get the solutions of this. And so this is the frequency equation. Now we want the eigenfunction. I'll show the solution of this on the subsequent slide. But now let us see the eigenfunction also, or the mode shape associated with this. So earlier we had equation which were in terms of C1 and C2 only, because we reduced. So one of this equation, if we take, and so this equation we can able to write C2 in terms of C1 because it is homogeneous equation. So this can be solved as C2 is equal to C1 and some. These are all constant term. There is no x involved here. Now this equation, now this is C2 and C1. So in our original equation, if I go back to this equation, so we already knew that this is minus C1, this is minus C2. Now we are replacing C2 with C1 also. So this whole equation can be written in terms of only C1. So when we use this, C1 is equal to C3 is equal to minus C1. So we got this. C4 is equal to minus C2. Then we got this. Now we are replacing this also with this expression so that we have the expression in terms of C1 only. So C1 is common, that can be taken common. So I'm writing that C1 as AR, and I'm attaching with all the beta R subscript, that is representing that whatever the frequency equation is giving infinite number of solution, beta RL. So those things I'm substituting here. So corresponding to the natural frequency beta R, if R is 1, here also we need to use beta 1. So this is the eigenfunction, orthogonal eigenfunction. So this is nothing but the, if you see in this, this is constant, but they contain the x value. This also contains the x value. So if we vary the x from 0 to L, we'll get the how the displacement is changing corresponding to that particular beta R. So beta R is related with the natural frequency. So if we are using beta 1, how the displacements are taking place in the beam corresponding to the first natural frequency, we can able to plot using this. If we are using beta 2, then we can able to plot corresponding to that particular natural frequency. So for different natural frequency, this variation of the displacement at different location of the beam will be different. So here, let me first show the plotting one. So these are the different mode shape for beta 1 is equal to 1, 2, 3. So how the beam will vibrate is shown here. So here you can see that I think this should be improved. So slope and the bending slope and the displacement should be 0 at the fixed end. Here also, here I think should be shown that slope also should be 0. So these are the 3 different modes of vibration of the continuous beam, which is cantilever, how it will vibrate in the first, 2, and 3rd mode. This is the basically plot of the frequency equation. Frequency equation is this. So we define, if we bring this in this side, so cos beta L plus cos h beta L plus 1, we define this as a function of beta L. And that function, if we plot, we will get this kind of variation. This is the beta L variation. So you can see that this is trying to become, because this is a semi-log scale, so this quantity is becoming 0 at these locations, and the x location of that is 1.8675, the first natural frequency, 4.69 second natural frequency, 7.8 third natural frequency. Slight difference is there because of the numerical error which we during the picking of this particular point. So these are the natural frequency of the system where the function which I defined here, is becoming 0. That is the roots of this this equation. So these are giving the natural frequency. So now we have seen how to obtain the natural frequency, the beta RL. So once we put the beta RL, natural frequency can be obtained from here. And these are the variation of the mode shape. So that is coming from here, which are orthogonal eigenfunctions. So here we need to vary from 0 to L values to get this kind of variation. So 0 to L variation, we are doing it. Now I'll take up another example of the banding of beam case in which the boundary conditions are different. Here we have both ends of the beams are free. So both ends are free. That means at x is equal to 0, bending moment will be 0, shear force will be 0. Similarly, at the free other end, at x is equal to L, same boundary conditions will be there. So these are the 4 boundary conditions. If we start with the application of the boundary condition in this, now whatever the procedure has been explained, we can able to solve for C1, C2, C3, C4. If we do the same procedure, we will get a frequency equation like this. This frequency equation looks similar to the previous one. Only thing I think -1 was here in the previous case. Now it is 1. So this particular equation is the frequency equation corresponding to this free beam. Both ends are free and vibrating transversely. So that is this is the frequency equation, and this can be solved for various value of beta. Here, because we have free case, so this is basically semi-definite system, unconstrained system. So here the beta 0 and beta 1, those also will be the natural frequency of the system. So there will be two 0 roots, and corresponding mode shape also we'll see how they will be. So, and apart from that, there will be flexible mode natural frequency apart from this 0. But because it is a unconstrained case, so we'll be having two natural frequency that will be 0. And corresponding to that, let us see the mode shape. So this is the equation. If we go back to the eigenvalue problem equation, this equation, or maybe I think I can go to this equation, because natural frequency beta is 0, so this term will be 0. So only this fourth order of the y is equal to 0. I'm writing in the next slide here. So beta is 0, so that equation becomes this. Now I can integrate this. I can a equation like this. Okay, d1, d2, d3, d4. If you just simple integrate, because first will be constant, then x, and then that kind of thing. So let us say this is the general solution. One derivative of this is giving us this. This prime is representing the derivative with respect to x. Two derivatives representing twice differentiation with respect to x. 3 is representing 3. So because we need to obtain d1, d2, d3, d4 from the boundary condition, and boundary condition require this derivative. Free case, we know that at x is equal to 0, bending moment is 0, so double derivative is 0. So if we do the double derivative 0, we'll get this. So here we are getting d3 is equal to 0. Similarly, at x is equal to 0, shear force is 0. This term is giving the d4 is also 0. At x is equal to L, we will get the same thing, or the equations will satisfy. We are not getting any additional information from the last two boundary conditions at x is equal to L. So from first two boundary condition, we got d3 is equal to 0 and d4 is equal to 0. So this equation will reduce to d1 plus d2x. So this is actually a rigid body motion. The superposition of the two motion, we'll see how it is superposed. So in the previous case, if let us say among this, if d2 is 0, if d2 is 0, then equation is yx is equal to d1. So that means the displacement of all the points on the beam is same. So that means if beam is here or here, so it's just as a rigid body going up and down. So this is called pure translational motion, and this is symmetric. Symmetrically, it is vibrating about the mean position. This corresponding to one of the natural frequency, which is 0. So we got two roots as 0. So one of the mode will be corresponding to this. Second case, let us take d1 as d2 minus L by 2. So if we put this, we'll get yx is equal to like this. And if we plot this, we'll get this motion or this motion. So you can see is the beam is tilting about this point once it is occupying this position, and then other extreme is going there. So is tilting about the center of this. So this is rotary motion, pure rotary motion, or the anti-symmetric mode. So you can see with respect to this, half of the beam is this side, other side is here, and on the other extreme, half is here and half is here. So this is called, both are called rigid body mode. This is symmetric mode. This is axis anti-symmetric mode, and this is pure translational motion. This is pure rotational motion. So that is corresponding to this particular mode. So corresponding to this, the previous slide, we have written the mode shape for first and the second zero natural frequency. Now the eigenfunction. So eigenfunction again can we can able to replace the whatever the constants as we did for the cantilever case, and the eigenfunction for this case will be like this, in which you can see the sine hyperbolic, cos hyperbolic functions are also involved. Okay. Orthogonality condition. Orthogonality condition, especially for the rigid case. So you can see that here I am starting from 2, 3. 0, 1 is corresponding to the 2, 0 value of the natural frequency. So y0 is the eigenfunction corresponding to the 0 natural frequency. This is for the flexible mode. Because this is a constant, we already seen. So this will come out from the integration. So once we are keeping the outside, so we are getting this equation. Now this equation is indicating that basically because because we don't have any external force on the system, so you can see this is something like inertia force equal to 0, because there is no external force in the system for free vibration. Second case, when we are taking the y1, which is axisymmetric or anti-symmetric mode, which was having x minus L by 2. So, and this is the eigenfunction corresponding to the flexible mode. So this is equal to 0 is representing that there is no external transverse moments are present in the system. So there's just so here we are indicating that even the rigid body mode are orthogonal to the flexible modes of the eigenfunctions, both the symmetric and the anti-symmetric. So the solution again we can define for the free Fay case like this the function I defined from the frequency equation. So I'm plotting this function with respect to beta L. So I'm getting values 0. So anyway, we have taken care of the 2 0 values, but here we are getting the flexible modes corresponding to this one. This is the flexible mode. So I can start from here. This is the first rigid body mode. This is the second rigid body mode. This is the flexible first mode. So this is 1.506 into pi. If you multiply, you get 4.7, something like this. So that is corresponding to the x value of this. So this is the root of this polynomial, this transcendental equation, one of the equation, one of the solution. This is the second solution. If we increase this, we'll keep getting the roots. So the second one is this one, 7.854. So this will be, if we multiply 2.5 into pi, you'll get this. So you can see there are 4 modes have been shown. This is the first flexible and second flexible. In this, there are 2 node positions. Here there will be 3 node positions. So as we'll go further and further, more and more number of nodes will come. I think there should be 3, 0, 1, 2, 3. It should be 3. So this is the code I have given for plotting the function. So especially this equation which is written, you can see 1 minus cos beta L, cos S beta L. So this function we need to change, and once we change this, we can get this plot here, and 2 locations we need to change this, which is marked as red. So basically, what we need to do, we are choosing various value of beta L, and we are finding this value and plotting it. So we have 2 value x and y, and we are plotting it, and then we are trying to locate where these values are having minimum value, and that is the algorithm which is there in that to locate this position, and then it gives directly the this roots, and it plots also. This plot is on that code only. And if you solve the any other assignment problem, you need to change this only, these equations. For different boundary conditions, we'll be having different equation. Rest of the things will be same. Okay, so I will just stop here. If you have any questions on this, if you have any questions on the bending of beam, because in this 4 unknowns are there, so equation becomes more complex, more lengthy, but procedure remain the same. So other boundary conditions case, I think already given in the form of assignments to some of you. So you can try out at least patiently obtaining those relations between C1, C2, C3, C4, and then getting the frequency equation and other. If you have MATLAB or Scilab, you plot it, otherwise no issue. So if you have any questions till now, you can ask on this. Okay, so I'll take up this enclosure theorem, which we already studied in the case of discrete system. So this is just extension of the whatever we studied. Now we are applying that enclosure theorem for the continuous system. Now here it is very important because here things are not simple. Solution of the eigenvalue problem is not simple. So the beauty of this particular algorithm will be clear more here. How we can able to get some rough estimates of the natural frequency using this procedure without solving the differential equation of the eigenvalue problem. So we define the eigenvalue problem like this earlier, in which we took the M operator like this. Associated boundary conditions we had like this, in which let us take the case in which the boundary condition is not containing the eigenvalue. Order of L is 2p and M is 2q, but here for present case q is 0, and number of boundary conditions will be p number at each boundary, and the order of differentiation also we know in the boundary condition will be 2p minus 1. So from this equation, if you see, if we divide MW and bring this side, so I'll get a ratio lambda. I'm defining as a lambda star. So if this U is, so instead of W, which is eigenfunction, I'm representing U. So W is the eigenfunction which we have derived. For two cases we have derived. If we put the U as eigenfunction corresponding to one of the natural frequency, the ratio will give me that particular natural frequency or the eigenvalue. Is eigenfunction. If we take the rth eigenfunction, we'll get corresponding rth eigenvalue. Okay, but what will happen if we don't choose the u as eigenfunction? Because a priori, without solving, we don't know the u. We don't know the eigenfunction. So if we choose something else, what will happen to this ratio that we want to see? So as in the discrete system, we chose the eigenvector arbitrarily, and we try to get the ratio of this. Similarly, here you will choose not the eigenfunction, will you choose the other function that is called comparison function. I defined earlier comparison function is which satisfies all boundary condition of the problem and is differentiable up to 2p minus 1 up to that. It should not vanish if we difference that much times. So this comparison function only we need to ensure that it is satisfying the boundary condition. There is no need to solve the eigenvalue problem to get the eigenfunction. Just by using comparison function, we'll get some ratio. So that ratio obviously here because this is function of u is function of x, the length of the beam. So if we vary the x, the different ratio will get. So among the different ratio, we need to find out which is the maximum ratio and which is the minimum ratio. And correspondingly, we can say using this enclosure theorem that one of the eigenvalue will be between these two minimum and maximum value. It will enclose one of the natural frequency or the eigenvalue of the system. So the enclosure theorem which we studied for the discrete system is exactly same. Only thing here we are using the continuous system eigenvalue problem formulation. Now let us see this through one example. So cantilever case, here we are considering the axial vibration. For that we know the L operator is second order differentiation. M operator is this. Now what is the boundary condition? At x is equal to 0, displacement is 0. At x is equal to L, the force is 0, so that is representing force is equal to 0. So these two boundary conditions are there. Now we need to choose comparison function which will satisfy these two boundary condition. So let us take a comparison function. So this choice of the comparison function is arbitrary. one can choose any value, any function, but we need to ensure that this should satisfy the boundary condition. So what is the boundary condition for, let us say, cantilever case? At x is equal to 0, this should be 0. So if you put x is equal to 0, is 0, so it is satisfying the boundary condition at rigid end. At x is equal to L, the derivative of this equal to 0. So if we take derivative of this, we'll get this. At x is equal to L, if we put, we will see that I think this should be L square. This should be L cube. There should be one more L here. Yeah, because here L cube is there. So if we put L is equal to x is equal to L, this will give 0. So that means it is satisfying this boundary condition as well as this boundary condition. So that is the requirement of the comparison function, that it should satisfy all the boundary condition of the problem, and it should be differentiable up to 2p minus 1. 2p minus 1. So here p is to 1, so it should be differential up to 1. So that is anyway, if you differentiate once, this will not vanish. So that means it is satisfying our requirement. It should be differential up to 2 or up to 2p. So even that, if you differentiate twice, it should not vanish. It should be differential up to 2p because L operator is having that much differentiation. So now L operator is in the here we are having L operator and this. So now we are obtaining this. So if we operate L operator on W, which is like this, if we differentiate twice W, we will get, after simplification, this. Similarly, if we now we are putting directly onto the this enclosure theorem. So this by this, and this we already evaluated. W is this one, so directly we can keep. Now we can take some common, because x by L is common. We cut some common terms, and if we simplify, we get this. So the lambda star corresponding to the eigenfunction, the comparison function, becomes this. Now you see that it contains x, and x can vary from 0 to L. So if we put 0 here, so we'll get this 0, so 2. So that means 2a by rho L square. If we put L here, this will become, if we put L here, this will become 2, so this will be 3. So 3. In between, if you put the x is equal to any value, they will be between 2 and 3, the coefficient 2 and 3. So that means this is the minimum value which we'll get from this ratio, and this is the maximum value. In between, if we put x value, they will be in between. So one of the natural frequency should be there between this and this. And if you go back to the solution of the cantilever case, which we already solved using the closed form solution, the correct exact value is this for the first natural frequency, 2.4674. So it is enclosing, it is getting enclosed between 2 and 3 coefficient. So you can see that just by choosing the comparison function without solving the differential equation, we could able to get some guess value of the one of the natural frequency. So this is one of the example. In the next class, I will take up the Rayleigh's quotient and other thing, and then we'll be entering into the approximate methods. So if you have any questions on this, what have I covered, you can ask. Okay. So on onwards, mainly we'll be we'll go for the approximate method or discrete system, and the continuous system also in the next 4 or 5 lectures. But in the next class, I will first explain the Rayleigh's question for continuous system. Then in the next chapter, that is sixth chapter, we'll be taking different methods which are available for solving the approximate solutions. Because especially for continuous system, we have seen that the equations for more complex geometry and the boundary condition becomes more difficult to solve. So there has to be some way out to get the some approximate natural frequency. So those 4 or 5 methods will cover in that chapter. So if there is no questions, I will stop here.